Okay, good afternoon. Let's work a problem to start off with that addresses some protecting group strategies. And it's, in principle, a very simple problem if you look at the strategic disconnections. And the question is to turn this into that. Sorry, I ran out of space. These bolts are shorter than in 100 Lewis, which has a phenol function at the end and carbonyl and this protected diol as the acetal. And so again, like with all these problems, you should look at left and right and see what's been added, what's been subtracted. Is it cyclic, acyclic, is it ring closure, and the like. So here it's fairly simple because we have 1, 2, 3, 4, 5 carbons. And if you look at what's going on here, and you see the similarity of this function here with this, it's 1, 2, 3, 4, 5 carbons. I lost one right here. Yeah, that is because the board got shorter. Gotta maybe do this structure. All right, this is better. We got 1, 2, 3, 4, 5 carbons here, which means that somewhere along the line we have to make this carbon-carbon bond, and this piece has to be is given to you in any form to allow this disconnection. So retrosynthetically, you would cleave there. And that's it. And we have many ways of doing this connection. As you know, one can have, for example, a grignard attacking an aldehyde here that gives you the alcohol, and you oxidize the alcohol. That's 2 steps. We have shorter ways now of doing this. The last few weeks have shown us how to make ketones selectively from nitriles and the corresponding grignards or alkylithiums, or from acyl halides with cuprates. So I'm going to pick arbitrarily an acyl halide and a cuprate. So I'm going to retrosynthetically disconnect this such that we have this piece here and the copper lithium reagent. And on the right, this means that we would have to have, formally at least, an acyl halide like that, okay? And so formally this would couple, it would make that bond. That sounds good, except that an acyl halide will react with the alcohol function. Moreover, the cuprate will also react with an alcohol function. Okay? So we have a problem with this being really a hindrance. Protecting these two guys seems to be already indicated in the product here, so that's no problem. It's actually given away to you, because clearly making a cuprate, which has to be made by the corresponding alkyl lithium, would not be possible with the 2 hydroxy functions there. So it's already given to you that the best way to protect those is just to use the fact that this is a diol, a 1,2 diol derivative, and you just treat it with acetone to protect it. So the problem is over here, we can't use this per se, although that's what we're aiming for in principle. Okay? So the solution is to obviously start with a derivative of this carboxylic acid derivative that allows you to protect the OH function. And so a good one would be to use, there are several, but I'm just going to pick an ester. And protect. Now the normal protection for alcohols that we've learned so far until last Tuesday was to use tertiary butyl ethers. Well, I shouldn't say normal. Up to now it was normal. And that was the only protection, where we took alcohols with tertiary butyl alcohol and acid, mild acid, just mildly acidic conditions, under which conditions you get protonated on the OH and the water leaves to make tertiary butyl cation. And the tertiary butyl cation then attacks the OH of the alcohol you want to protect to make the corresponding tertiary butyl ether. And the deprotection was just dumping in a lot of water to hydrolyze it back. Okay? That is a possibility. We could do this here. But now we are faced with a problem in the final product. When we've done the coupling with the protected acyl halide derivative, we wind up with a product that has an acetal as well as a T-butoxy function at the end. And the required product is the corresponding phenol. So we would have to hydrolyze off the tertiary butoxy with acid. And that would also hydrolyze the acetal. Okay? So we can't use that as a protecting group strategy, because the deprotection step will not selectively deprotect the phenol OH. It will deprotect everything. Everything will come off. And instead of the desired selectively protected product on top right, we would get the corresponding triol, where we have the liberated diol function plus the phenol, okay? Which was not the aim of the synthesis, because in the synthesis people wanted to keep one side protected so they could work on the other side of the molecule and then unravel the diol much later. Okay? So for that, we now have a second way of protecting that gives you a protecting group that is acid and base insensitive. Okay? It's stable to acid and base. And that's the one where we, with a mild base, dilute sodium hydroxide or sodium carbonate, and a benzylic halide, we make the benzyl ether. Okay? That benzyl ether is stable to acid and base, and we remove it under conditions that won't touch the acetal. We remove it by catalytic hydrogenolysis. Okay? So that the solution is to use this, turn that into the acid chloride, by hydrolysis of the ester, under which conditions this is stable, and then thionyl chloride. And that gives you the desired protected acyl halide, which is internally protected. It won't touch, it won't touch this oxygen because now the OH is removed, and this thing will then react with the cuprate here in the desired manner to give you the coupled product, and then you do the catalytic, the removal of the function. So in the end, the crucial coupling step would be not with this guy, but we would react that with this species down there, which is the protected acyl halide, to make this bond where you get this in a protected form, namely as the benzyl system. And then you deprotect by catalytic hydrogenolysis using palladium on carbon. So we have that capability now of using what's called orthogonal protecting groups, where orthogonal means that the deprotecting steps are mutually exclusive. They don't touch the other function. Okay? You selectively remove one protecting group without touching the other protecting group, both protections being protections of alcohols in this particular case. Okay? So that's where the usefulness of this benzyl oxy protecting group comes in that we discussed on Tuesday. Yeah. All right, so let's resume with the chemistry of phenols. We started discussing what the benzene ring does to attach substituents. And in particular, in this section, we are talking about what does the phenyl group do to the attached OH function. Okay? As opposed to what we did before in chapter 15 and particularly 16, what does the OH function, the hydroxy substituent, do to the reactivity of the benzene ring? And so one thing that the phenyl ring does to this OH function, it affects its acidity. Phenols are alcohols after all, but there are some slight variations. They do react like alcohol, so in that respect, this is the following section, the remainder of this lecture, by and large, actually, is review, at least with respect to the alcohol reactivity of phenols. But there are some differences, and one is induced by the fact that this is now not an alkyl substituent, but a phenyl substituent, and this means that this carbon is sp2 hybridized. The other effect is the delocalization into the benzene ring. And so what we measure when we look at the pKa of phenols, we find that they are 5 pKa units lower, so that's 100,000 times more acidic than a normal alcohol in water. Okay? And the acidification derives from the fact that this carbon is sp2 hybridized relative to sp3 hybridized, as for example in cyclohexanol, electron pulling, so inductively it pulls, makes this proton more acidic. And the corresponding product is resonance stabilized by delocalizing the negative charge into the benzene ring. And this drops the pKa unit measurement down to 10. So 10 is a good number that we've encountered before. It's the same as ammonium. So in our continuing theme of remembering roughly pKa's in increments of 5, add phenols to your ammonium number. Okay? And you can see how this negative charge on the oxygen is stabilized by delocalization. This is, after all, nothing else but a glorified enolate. Okay? But it's an enolate that puts the negative charge on this carbon and can keep on going in terms of delocalization by putting it on the para carbon and then again on the other ortho carbon. So we have 4 resonance forms that describe what's called the phenoxide ion, which is nothing else but an extended enolate ion. Okay? And one can look at substituent effects on the acidity. Obviously, if you put electron withdrawing substituents on the benzene ring, the pKa should drop. In other words, phenols should become even more acidic, okay, because you're removing electron density from the vicinity of the OH. And if you're doing this with substituents that are capable of resonance with the negative charge that's sitting on the oxygen, and you now know where the substituents have to be, either ortho or para, in order to be able to communicate with this group up here, then there's an even more pronounced acidifying effect. And therefore, when you look at para-nitrophenol, you find that the pKa now is dropped to 7.15, about a factor of 1,000 lower or more acidic compared to phenol itself. And you can readily see why the OH, when the proton comes off the oxygen, the O- shows the usual delocalization that we saw up there, except that there's an additional resonance form where when the negative charge is at the para position, it can now swing into the NO double bond of the nitro function. As you may recall, nitro is kind of special. We saw this already in chapter 1 in terms of Lewis structures. The nitrogen, in order to preserve the octet, this has to be, the bond to one of the oxygens has to be a single bond that is dipolar, okay, where this is N plus and this is O minus. You can't take this electron pair and push it in here to make it charge neutral, because that would give the nitrogen an electron D set. And D sets are not allowed for second row elements. There, the octet rule strictly holds. Only for the next rows can we do what's called Lehman shell expansion, formally at least, like for sulfur and phosphorus and so on. So we get these dipolar forms. But the bottom line is that you can delocalize that negative charge from up here down to the oxygen here, and that makes it even more stable because you're spreading out the negative charge further in space. And you can keep on going. By the way, you also know how to make para-nitrophenol. You just do it by electrophilic nitration, electrophilic aromatic substitution. The first nitro will go para for steroid reasons. If you keep on nitrating, you will get 2,4-dinitro and eventually trinitro. And as expected, now we have a second potentially, or actually resonance-wise stabilizer of the negative charge here. So the pKa drops down to 4, and with 3 of them, it drops down to 0. 0 is already is close to mineral acid. Okay, so indeed, this guy here, 2,4,6-trinitrophenol, common name is picric acid. It's been used in the leather industry and the like, but it's also an explosive. So at one time, it was used in mass production to be used in mining as well as warfare applications. This guy, when you put it on your skin, actually will start stinging very quickly. So this is a nasty camper also, and that's because these 3 nitro groups make this phenol very, very acidic. Now that's really extraordinary. If you look at this, 0, normal methanol is 15. Okay, so this is an extraordinary acidification, which is a result of this resonance capability of the nitro group. Of course, if you start putting in pushers, starting with just a mild pusher, a methyl, an inductive pusher, make the benzene ring more electron rich, then the pKa will go up, because now the proton is more happy sitting on this oxygen, or conversely, the negative charge is now less happy because it has to delocalize into a benzene ring that becomes more electron rich. And so the more methyl groups and the like you push on there, the worse it gets. So with the appropriate tinkering, you can literally titrate, design the pKa of a corresponding phenol. A phenomenon we've seen starting in chapter 8 with the alcohols, and then we looked at it again in several other places, including the carboxylic acids, and then on Tuesday, I think, or last week, for the amines, the ammonium salts. Okay? So that's a general phenomenon that you can tinker with the pKa by pushing or accepting substituents. So now let's go to a subject that is of great interest, namely how do we make phenols? And we've seen phenols all over the place, and we've used them in a variety of ways, but at no time have we actually been able to make a phenol. Okay? Some of you have asked me about that in synthetic problems when they come and we work some problems. They ask me, well, how do you make the phenols? Can you make the phenol from benzene? Okay? And we didn't have a solution to that. And part of this has to do with the fact that it's very difficult. You can't, ideally, what you'd like to do is have an equivalent, a functional equivalent or reagent that will produce OH+. Okay? Then you would have a great electrophile, just like NO2+, the nitronium ion, or the acyl cation in Friedel-Crafts acylations, that would do electrophilic aromatic substitution. And the problem is, this is not easy to make. In fact, per se, you can only make it in the gas phase. There are, in recent years, people have developed chemistry where you have what looks like a hydroxycarbocation equivalent, but none of these reagents have really turned out to be very general. Okay? So this is really a problem that people are still working on, to get something simple, cheap, that is essentially does a direct hydroxylation. Instead, in order to solve the problem, because this clearly is an important synthetic problem, introducing an oxygen into a benzene ring, people have come up with a variety of other solutions. And by the way, of course, the reason that hydroxycarbocation is a bad camper is because you're putting a positive charge on a highly electronegative oxygen, and it absolutely doesn't like that. Notice that this differs from OH-. OH- has an extra electron pair on here. So OH+ is a sextet with a positive charge on it. Okay? So that's a very bad unit. So that's why it doesn't like it. Okay? So it turns out that there are various strategies that allow you to displace formally, not mechanistically, it's mechanistically more complicated, that formally allow you to displace a leading group, such as a halide, with OH-. Okay? But it's not what one would ideally want to do, namely like an SN2 type reaction. We know that this is not possible because we already learned that we can't do SN2 reactions on an sp2 hybridized carbon in an alkenyl, in a CC double bond. Okay? So this has to be more intricate mechanism in order to pull this off. But formally, that's what we're doing. We're starting with a benzene ring that bears a leading group, and by a mechanism, one of several actually, we can displace that leading group. And so what we'll learn is 4 mechanistic possibilities that allow you to do this. One is actually what's called nucleophilic aromatic substitution. That is, the nucleophile, in this case hydroxide, actually attacks the benzene ring and generates an anion, and then the leading group leaves. And this is only possible when you have strongly electron withdrawing groups on your benzene ring, ideally resonance electron withdrawing groups. That makes the benzene ring sufficiently electron poor that a nucleophile now, with its electron pair, can add and kick out the leading group in a subsequent step, and we'll see the details of that. Without any electron withdrawing groups, under very stringent conditions, either high temperature or using an extremely strong base, we can actually replace the halide by an elimination addition sequence. That is, the base eliminates HX to put in a triple bond into the benzene ring, a terrible species, really, a highly reactive compound that's called benzyne, or dihydrobenzene. That is so reactive that it then grabs the nucleophile in order to get rid of the triple bond, which is a highly stabilizing unit. So we'll see that. And then we'll come back to the super leading group N2, okay? Namely phenyl or aryl diazonium salts that can be made. There, the diazonium salt is stable enough that you can isolate them. And when you heat them up, they will eventually kick out N2. And if you do this in the presence of a nucleophile, for phenols it will be water. The phenyl cation is trapped and you get the phenol. And then there's something new, namely one can also do this using palladium catalysis, which is really a fundamental breakthrough in this entire chemistry that simplifies all your mechanistic and synthetic thinking. So I'm sure you will use that extensively if you can in a synthetic application. So let's look at these 4 possibilities. So the first one is called nucleophilic aromatic substitution, often called ipso substitution, because the nucleophile has to attack the carbon that bears the leaving group. So in this case, it's the substituted carbon. And you will notice that this is the negative charge equivalent of electrophilic aromatic substitution. There, it was E+ that attacked, making a cation that's delocalized in the ring and stabilized by electron-donating substituents and the like. Now we're turning this around and doing this with a nucleophile that makes an anion. And as I said, this only works if the benzene ring bears electron withdrawing groups, particularly well if the electron withdrawing groups are resonating, and they can resonate and stabilize the negative charge that is evolving when you add the nucleophile to this carbon. And place a negative charge here, or here, or here, and when it's sitting here and here, obviously it can delocalize into the nitro ring. When you do that, you can do a displacement. It's a 2-step process, which, in a way, this is a good way of thinking about it, is reminiscent of the nucleophilic addition-elimination mechanism of carboxylic acid derivatives, such as a acyl halide. So if you focus just on this piece of the molecule and imagine this to be oxygen, you can see that there should be a nucleophile adds, electron pair kicks out to what would be the oxygen, and then it comes back in and kicks it out. So the oxygen makes this possible because it's very electronegative. This system makes it possible because the negative charge doesn't sit just here, but it goes around the ring and delocalizes into the nitro group. But the principle is the same. It's addition, the negative charge is enabled, and then it comes back and kicks out the leading group. So an example is here, if you heat up just sodium carbonate, so this is pretty mild basic conditions, with dinitro chlorobenzene, you go to the corresponding phenol. This can be done with other nucleophiles. We'll look at amines every now and then because they're so similar to water in this respect, and amines will displace and you get the corresponding amines. And you notice the yields are excellent. Okay? So here's a mechanism that I already described in words. Here it is in structure. So the first step is the nucleophile attacks, and indeed you kick the electron pair to the neighbor. Okay? This looks very much like electrophilic aromatic substitution, except that the electrons flow in the other direction. And what's left in the ring is a plus charge that's delocalized. Here we're flowing differently. We're flowing not towards what would be